you advertised a major breakthrough, so this had better be major.
Well, that's the plan. I mean, refrigeration's been around for 100 years, so you know what's new. The principles are the same, but we have seriously miniaturized it. So, and that has interest in the medtech space that we're talking about here today. Basically, it's not your grandma's icebox. I mean, these technologies have been around for a long time. You can see the system on the left is a bit arcane. And now we have a cooling system
That's very kind of
that,
this picture. It's almost
excuse
like
me?
this picture is very amusing to me because it's almost as though this particular image you've chosen is said, hey, everybody, look now, it's 1960. I'm thinking there
Well,
was probably another 60 years in there you could have squeezed into this image, but have at it. It's your show.
that's coming. And right now you can see the system on the left. We have a compressor the size of your fist that now cools the refrigerator in our lunchroom. So we have seriously miniaturized the system. And but our history is we didn't come up with this all on our own. Back in 1990, a requirement flowed down to us from the military for dismounted soldier cooling, and they needed a small refrigeration system to cool soldiers in very hot environments, and that triggered the development of the small compressor that we use today. So over about 10 years, we worked on systems for dismounted soldier ordnance disposal suits. Those guys overheat in those, and also chem bio cleanup. But those applications drove the miniaturization of the compressor and also of the system themselves. And as we pushed forward with this, we went into production with what now is a very small compressor that, let me get it on the right side here, that you can see in my hand.
Mhm.
And that unit weighs about 1.2 pounds. And it essentially, let me see if I can pick this up here, replaced this, which is the size of a football and is the normal compressor that's in the size, it's in your refrigerator at home now.
How much is that like? Because you said
It,
1.2 pounds, and then you made these great exertion
it,
noises, and I was
it,
like, Jim, you gotta exercise, man.
Yeah, it's a little over 10 pounds. The grunt was for exaggeration, but the miniaturization really does allow a whole new array of applications for refrigeration to be used. And so that we replaced this large compressor with the small one. They have the same size and the same performance. The small compressor is variable speed, which comes to what it allows us to do is very accurately control the temperature. So with a simple interlock to the medical device, in this case, we can take a PID signal, vary the speed of the compressor, and dial in a temperature at plus or minus a half a degree C. So now those systems can be embedded in the medical equipment rather than sitting on the floor taking up a huge amount of space in a treatment room.
I would love it if any of the folks on the call left a comment or raised their hand and told me if what he just said makes you go wow, because it sounds impressive to me, but I don't know anything about cooling. So hey, we took this 10-pound thing and made it 1 pound. Sounds good. And other benefits you mentioned, okay. Is this like, that's nice, or oh my God, now I can finally do this technology that has been previously unavailable?
It's a game changer.
I'd
If
love it if
the
anyone agrees or knows and
okay,
comment, but please go ahead. Tell me about
okay.
why it's game changing for someone who knows nothing.
Right. Basically, by miniaturizing these systems, we can bring a very high cooling capacity and integrate it inside the medical device, and keep the very high efficiency that refrigeration provides. And so, what we're displacing are chillers that take up 2 or 3 feet of floor space and weigh 80 pounds, with a system that weighs 5.5 or 6 pounds. And is essentially this size. This is a complete refrigeration unit. That's the guts of a chiller. And so what that does is it lets us integrate cooling directly into a medical device without having this standalone unit taking up a huge amount of space. The other class of components that, or of cooling methods that we're displacing are thermoelectric. And not in all cases, but where the cooling load is above, say, 100 watts, or there's a large or a very cold temperature or a big temperature difference between the cold side and the hot side, we're displacing thermoelectrics for several reasons. One is now it's small and we can be integrated into the equipment like a thermoelectric can. But also, because our efficiency is in the neighborhood of 5 times better, we don't run into power draw problems from a single outlet. We have, for certain customers, displaced thermoelectric because they literally couldn't draw enough power out of the wall plug to meet their cooling requirements with a thermoelectric. And it's because our efficiency is so much better.
Let me stop you for a moment. Eddie, you had a question.
Yeah. Hi, Jim. Just curious, what you keep talking about refrigeration, but how low can you achieve with in temperature terms, and how quickly?
Okay, certainly. We have systems that on the cold side run down to minus 40 C in a single stage. Those can, and a number of our customers couple those with a thermoelectric. So most of the heavy lifting is done by vapor compression, and they can take it a little bit further with a TEC device that's coupled to it. That would allow even lower temperature or to help improve temperature accuracy at the on the cold side, on the cold surface. We have systems that at 140, 125 F on the cold side in our military environments, where we've miniaturized environmental control systems for electronics. We enable routers and servers to run that are designed to run in the corner of your office building. We allow them to function in the back of a Humvee. And so we have range of temperatures on the cold side from minus 40 up to 125. Yeah.
Okay.
So I hope that covered your question, but.
Well, yeah, my previous company I was involved with was dealing with generating X-rays, and one of the ways that you need to do that is creating the vacuum, and one of the ways to create the vacuum is to bring the temperature down. So, so that little thing can get you to minus 40.
Yes.
Wow.
Yeah, we have systems in often. In that case, a lot of those systems they run that cold are for integrated circuit burn-in, and they do thermal cycling. So we have the cold plate up on a flex line, and but we can run that single stage at minus 40.
Interesting.
Okay. Scott, you got something?
Yeah, I do. Sorry to kill your presentation, Jim, but one other follow-up question kind of on that little refrigeration unit that you just held up, right? That includes this mini compressor. What type of BTU capabilities does something like that have?
I've got slides for that, so you'll have to wait. Okay. I get that question all the time. What's the capacity? And the capacity always depends on the temperatures. And the curve will explain that in very short order.
Okay.
Don't make us wait, Jim. Go to that slide.
Yep. I'll skip that one. Here's the slide that we just talked about. So I need to move you guys so I can see it. Here we go. So what you see down here, this is one of our systems. It's one of many, but it's one of our systems. What you see on the lower x-axis is the coolant temperature delivered from the unit. And on the left, we have the coolant capacity. And we have 3 different curves. These are ambient temperature. So you can see that the cold side temperature is a big driver on what our capacity is.
I'm sorry, the dotted line suggests that it could go as low as, but
the dotted line is with propylene glycol water mix, and those will go down to minus 15. We can go lower, certainly with a different. This is for a liquid chiller. For a direct refrigerant system, we can go a lot colder than we can with a chiller.
To negative 40 degrees Celsius.
Correct. So you can see that when you ask capacity, in every incoming inquiry I get, it's what's your cold side temperature, what's your hot side temperature, how much cooling do you need? And from there, we size the compressor, the heat exchangers. Those 3 numbers drive everything.
May I ask, this system's at 140 degrees Fahrenheit ambient. Does that mean you can put us in the desert and it will function?
Yes, we have systems on all over the Middle East right now with our military in the back of Humvees and MRAPs. We're a supplier to the Joint Light Tactical Vehicle Program with an air conditioning unit that cools kits on the back of that vehicle, and it goes up to 140 F ambient air.
I'm just curious because that's pretty unsurvivably hot.
Yes.
Is there anything on the market that goes higher than 140?
There are limits to the vapor dome with the refrigerants. So the maximum that we could go to is about 71 C. We have done systems in that environment and have to get out my calculator to make that conversion, but it's in the neighborhood of 165 F. And at that point, literally you can't get liquid out of the refrigerant. So that's sort of that's where the hard stop is on the upper ambient temperature.
Thank you. Scott?
Just one other follow-up question. If we have time, I'd love to do a live like calculation on the fly. If you can, maybe I'll give you a use case, Jim, if we have time.
Oh, I can put my, I've got a compressor model that I use. It's often real time with customers. And okay.
Yeah.
Give me a moment. I'll have to.
Do you have any like music while Jim kind of goes to town here?
Yeah, let's see now. How to find it here. You see, now you can see how I organize my my world here.
Scooter, do you sing at all? Scott,
What's that?
you sing at all?
I do not. No.
I was thinking maybe we could harmonize.
Whenever I sing, my kids tend to give me grief.
Okay, what's your cold side temperature that you need?
So cold side temperature would be like the end temperature that I'm looking for. Is that what you're?
Yes. Yeah. Whatever temperature you need delivered.
45 degrees Fahrenheit. So
Yeah,
sub 5 Celsius, but let's just call 45 Fahrenheit.
Are we cooling with air?
Water.
Okay, so this is water. So I need to use a 10 degree, sorry.
I was wondering if you have a screen that you're looking at, because we're only seeing your PowerPoint.
I apologize.
Don't apologize, just pointing it out.
Got it. Let's see where to go. Here we go. Oh, I need to stop and then share again. Okay,
Yeah, you can share that whole screen, whatever's on, but
here we go. Oh, yeah. Can
okay,
you see it now?
You can see an Excel spreadsheet, yes.
Okay, my inputs are here. And so I've got my refrigerant type, I've got the compressor size, which we will play with as we could do this exercise. And now I've got my evaporating temperature. This is the refrigerant temp. Okay, so I'll calculate that. You've got a liquid. So I'm going to use a 10 degree F delta T because I've got to run my refrigerant colder than the liquid to get heat transfer. And then, and what was your delivered?
45.
45. So 45. Okay, so 45 minus 10. And what's your ambient air temperature?
Let's go with 68.
Okay. All right. And so how much capacity do you need? Because I'm going to tell you how much power it'll draw when we're done here.
Capacity meaning volume of water?
How many watts of cooling are required by your application?
How do I figure that out?
That's
non-engineer
often,
like myself,
it's often difficult. We can guess. I'm going to choose one of our compressors. So it's a single 1.9 cc compressor. It's just one of the compressor models. And
Jim, if it helps, I need to cool about 50 gallons of water as fast as possible.
I would need to know how quickly it needs to be cooled in order to calculate.
30 minutes ideally.
Okay. Can't do that in my head. That's a sidebar calculation.
Okay.
That we don't want to do here. So what I can say, basically you just take your time and the total volume of water, take the heat capacity and figure out your rate to get the watts. It's not in here. It's a sidebar calc that I would do.
Okay.
So for this to get 380 watts of capacity, I know I can run my compressor at 6,500 RPM. We can use R134A, but we do have a whole range of the new green refrigerants that are being required in the EU, and some of our customers are switching to those, and some aren't. And then, so that system will do 400 watts of capacity at those temperatures. And, you know, if we go to a twin 1.9 compressor, I can give you 800 watts at that. And we have other compressors that are not our own that we also integrate if more capacity is needed.
Okay.
So we have a range of these very small ones, but a number of our customers, after working with us, have used us for other custom systems that just need more capacity than these little guys can do.
Got it. Thanks for that. And just, and I don't want to toot your horn, Jim, for you, but I've talked to a fair amount of people like in this space for what I'm trying to accomplish, and you definitely know your stuff. There's no doubt.
Well, thank you.
Yeah.
It's, you know, one of the things that we really do pride ourselves on is this front end conversation is so important, because extracting the cooling load is not easy. And so there's a lot of teaching that takes place at the front end, and then the guys on the team just follow through. They can miniaturize these things and customize that in a whole number of ways, but it's all driven by the requirements.
I know this is silly, but I kind of feel like a proud papa right now. It's just family getting together around the table. Jim, you're our go-to cooling guy.
Well, thank you. I love this stuff. I love what we're doing. You know, one of the things that drove me and that has been really exciting for doing this for years, I did R&D with a passion to see, let's carry something forward and get beyond the R&D world to get it out there where it's going to do some good. And we've done that. I mean, we were R&D organization, made the switch in 07 when the compressor came on board. And now we take these things and we're cooling cables for electric vehicles. We're doing medical devices across the board, a lot of medical aesthetics and things. And so it's very exciting, really, to do this.
What is your functional expertise? Are you an engineer?
I'm a mechanical engineer. I did a lot of material science and a lot of electronic packaging. In working with the materials guys, I focused on thermals because it was a part I could bring to the table. So I learned a lot about packaging through the R&D phase of my career, and have kind of brought that to bear on the vapor compression cooling that we do now.
Anytime I hear the word packaging now, Mrs. Gates has trained me to think about her first. So I promoted her even though she didn't ask to be. And here she joins us from outer space on mute. I thought maybe we'd have a quick sidebar on packaging. I wouldn't have thought of it in the same context of what you're doing in packaging, but are you saying that by putting the compressor in any kind of box, like a refrigerator, that's the package?
I kind of shifted gears a number of times there in that. With electronics packaging, it's how you tie the electronics together with the thermal management. And that background in the thermal management piece is what has brought it to bear on how we package these systems. So it's not really
in today's world, or it is?
There's a lot of the packaging that takes place is how we integrate into the custom equipment. And so that it's really how we interface controls in the sheet metal. The packaging is the guys put together. We ship sub-assemblies to contract manufacturers primarily, or directly to the medical device integrators themselves. And so that part gets handled by the production team.
Mm-hmm. Ms. Gates, relevant for your world or no?
Oh yeah, it would be, but I'd have to know a lot more about the electronics to understand the shock and vibration issues that might occur and how they want to keep it undented or printed or different pieces together with it. When you're talking about the kind of systems he has, it gets more complicated. And then trying to optimize the stuff that goes into it so you can actually maximize the efficiency of his units for whatever you want to have it cooled or whatever. There's a lot involved, and it's sort of fun to make it all work together. I've only had to work with trucks and enviro containers for that kind of work, so it just depends upon what. I don't know exactly how his system is. I'm sorry, I came in late. So
No, this is fine. And where there is a fit with that, and we have looked at cold chain and using our systems for cold chain and have looked at that on and off for a number of years. The big issue we have with our systems to extend cold chain beyond what you can get with a phase change material plus insulation or some of the other approaches that are used is with our small systems. Where do we put the heat? And when all those boxes get stacked together, where do you, it has to be ambient, it has to be air to dump the heat into, that has to be then carried away. And so we're good for the last couple days of that and could be used for smaller. And we have a couple projects right now where that mobile cooling that needs to go beyond what you can get with phase change plus insulation becomes important. And so for that, and for all of our applications, really, we depend on our industry partners to drive the requirements. And then we open up the possibilities for what it is that we can really do and talk about what the design drivers are for a particular application and bring our experience to bear. And so in the packaging world, it would be cold chain. And I think there's a place with COVID here as well for that, with where we could seriously extend small package shipments beyond what could be attained right now with passive approaches.
Yeah, that would be sort of nice with, especially with pharmaceutical deliveries that are supposed to be cold, and just have a big unit
right.
in every truck or whatever. You could put the stuff in so people could get it at a right temperature. What you're talking about is the heat dump we had to learn in food science when we were packaging our foods and making sure all those numbers came together and you could get the heat out the way you needed to. Yeah.
There's been some inquiries on that as well, with some of the rules that are in the process of flowing down to that industry to maintain temperature control through the whole supply chain. And we've gotten some inquiries along those lines as well. And it's a matter where the pressure of the law change drives a change. I don't think that pressure's gotten high enough to force the change yet. It's just
No, but it's coming. There's lots
Right.
of lawsuits out for things, so hopefully
Right.
that'll be done before my sister goes blind because they won't deliver her medicine at the right temperature. Because it's
Okay.
only her going blind instead of dying. They don't consider it a crisis situation.
Hmm.
And I'm going,
Oh.
what? So I'm helping her with buzzwords and stuff with her work.
Thanks, Jan.
Yep.
Jim, do you want to return to our previously scheduled?
Yeah, let me, I guess I
presentation?
need to go back here to, yeah, there we go.
An excellent job fielding those questions. Thank you.
Oh, it's really, I get involved in the front end of these conversations. So this is a lot of what I do with our incoming requests
Mhm.
is handle questions exactly like this. And I always go to this curve when I get, well, what's my capacity and what
I'm
temperatures
curious
can
to
you do?
as you know, I do marketing for a living. Once you're having these kinds of conversations, what percent of the time does the company, if they choose to go forward with any project, do they choose your company? Because like Scott said, you obviously know what you're talking about. I don't have a good sense of your competitive set. I don't know how
Okay.
often people hear of you. What are maybe some of the big names that you consider to be chief among your competition that people may have heard of?
Because we are the inventors of the compressor. So in this very small space, there's a couple of people that use that small compressor, but we really are the leader. We have the most experience with it. But we're also
You license the technology? Are there people who are basically white label, they need some of your patents to run their things, so you're making a profit even when they don't choose Aspen?
Our differentiators are the quality that we bring. We do, when we build a refrigeration system, we don't make commodities. And so in this sense, it's the medical community that needs the quality, that needs the accuracy, that needs the features that we bring, our target. And let me go back. It's these markets right here that use us. So we've got medical device, and this is right from our website, but medical devices, laboratory, and laser. But in all these cases, are the systems that we make are embedded in the equipment. So the small size and the integration. So the customization is a big differentiator. Not a lot of refrigeration companies will do that. And so the differentiators are small size, high capacity, efficiency, and the customization that we bring. And so these markets, you don't see countertop or commodities in here, and we don't do the large chillers that can be made in volume that aren't integrated. So I don't know if that explains it
Thank you.
properly, but that in every case we're doing something unique. Even our standard products have a unique position that often are used integrated as they are into the equipment. I touched on the different approaches that we use, where we have classes of liquid chiller and we do air cooling. And we ran through the example from the analysis sheet that talked about capacity of how a chiller would do it. But we also cool air. And in this medtech world, often it would be air cooling for laser procedures, where the skin needs to be cooled for medical aesthetics applications. And in that case, it basically the skin is kept cool so it doesn't overheat, and it can extend the procedure and for comfort measures. In the third approach, that we call it direct refrigerant. And in that case, there's no pump and there's no liquid to maintain. And so in this case, we can get to the very low temperatures, but we're eliminating some of the bill of materials from the system. For example, we can use a direct refrigerant in place of a liquid chiller. We don't need a pump and we don't need a reservoir. And we can hit lower temperatures. It's more efficient, and the maintenance basically goes to zero. Where the pump in a liquid chiller system is going to be the first element that would cause a problem. It's just simply not there if you go to direct refrigerant. So a number of our laboratory equipment companies are going to that, and even medical device companies are going to that to take advantage of those features. But you can't get that off the shelf. You need the customization and the engineer to engineer communication to get these sub-assemblies ready as you're going through qualification, ready to support qualification and then production. So a couple of examples. One of the examples that I chose for this presentation, we have Arctic cold caps. And in this case, they came to us and said, we want to use a small portable system to cool the scalp. And this system needs to transfer with the patient from home to the clinic and then back home again. So it needs to run off batteries, needs to be very efficient. It needs to provide a uniform temperature uniform temperature to the scalp. And what they have done, what we're doing now with these is in the process of displacing ice-based systems and frozen gel cap systems and these large cooling systems that take up space in the clinic and slow down the throughput at the clinics. So as we've developed this product, we took and modified one of our liquid chiller modules that you see in the bottom center here, and it's now integrated into a portable device that the patient can literally start cooling their scalp at home, transfer to the oncology clinic, and move right into the treatment room with this system in hand. It weighs about 10 pounds or so. And now the throughput at the clinic has gone up. It increases the efficacy of the treatment, and it provides a uniform temperature throughout the whole process that's controlled. And now the only way to achieve this is with an efficient refrigeration type system that can run off a battery for a period of time. Thermoelectric would not allow this to happen because the cooling loads are too high and the power draw would be too high for the battery life. So there's a class of applications that need to go mobile where we're creating new opportunities for medical device companies to take advantage of this technology.
Bringing Mark on, he has a question about Welkins cold cap.
Certainly.
What is the cost of it?
Hi, quick question. I was just talking to a friend in Canada who was using a cold cap that used an ice chest with dry ice in it. She had to rent it for $500 a month, which just seems, really expensive. How much does this little unit cost? It seems like a.
We're a bunch of mechanical engineers. So we get our requirements from the device companies. You could go to Arctic Cold Caps. They are rolling this out now, and I definitely would. It's a superior method to accomplish that that treatment. So I don't get into that part of it, but I can point you there. If you contact me, I can put you in touch with them
Okay.
and go that route. I just yeah.
I thought you just might have a ballpark, but I'll talk to them.
Right.
But thank
Yeah.
you.
Another very similar application is this same type of cooling can be used to manage the core temperature of a person. It can be used for a number of applications. And of course, this drove the development of the compressor to begin with, but it can be used for traumatic brain injury, stroke, post-operative, and we're working with a number of companies in that arena as well. But it's a range of applications that we're in the process of addressing. They use a very similar approach, perhaps at higher cooling load than the previous example that I gave. Another one that's kind of interesting to us is a product for medical aesthetics, which is a big arena for us where lasers are involved, and in particular cooling the skin. In this case, the customer did not want to use could not use a standalone chiller on the side, which is essentially as big as the entire unit that they are now rolling out. And so what it does is a laser treatment for medical aesthetics, and it also, so those laser diodes need to be cooled, and the patient's skin needs to be cooled as well for the efficacy of the treatment. So we made a very small pair of refrigeration systems for this unit that are now embedded. So these use a direct refrigerant approach. There's no reservoir, there's no pump in this. And so it made room for two of these units, and one of them cools the laser diodes, and the other one is used to cool the air that passes over a heat exchanger on the cold plate and runs the air right down the tube along with the fiber laser to the treatment point. And so this is another example of how we integrate these small systems and enable a much smaller unit to be put into a treatment room. At the same time, if we had used, and we have had a number of our customers come to us that have asked us to replace thermoelectrics in these type of applications, simply because the amount of heat dissipated from the thermoelectric unit was driving up the heat of the treatment room and causing one, discomfort for the patient, and two, the ambient temperature now in the room is rising and overcoming the air conditioning unit or the treatment room itself. And that in turn was causing thermoelectrics to fail because it couldn't keep up with the new higher ambient temperature that itself was producing. So it really is like a 3 or 4-fold effect of having the higher efficiency system in these units. Another application that came to us was basically field laboratory equipment. And in this case, a researcher had been studying insects, bumblebees, and in this case it's crickets, but the primary story was with bumblebees. And they needed to make them cull or bring them all back to the lab after gathering them all over the mountains. And then they would lose insects along the way. So they wanted to take the field laboratory out, the laboratory right out to the field. So we made this little battery powered unit for them that runs at minus 40 C on a battery or a very small generator that dramatically increased the efficiency of this field work that they were doing. But for this group, it's also an example of how small the systems can be made. And because it's battery powered, now we can talk about going mobile with the unit. sports medicine, and similar type applications come to mind for this.
Bringing Jan back, she had a couple of comments. Jan?
Yes.
Your comments that you typed in?
Oh, on the last slide, I saw lots of good shock and vibration work. So that would, for the product itself. So I was wondering, with your Halt and Hass testing, how much shock and vibration work you put into those units too.
Let's see. I honestly don't know. And the reason for that is when our expertise really is the refrigeration system itself. And so we typically will ship a sub-assembly like you see here, and either the medical device company or their contract it gets delivered at the contract manufacturer or the company itself, and they do the integration. So we don't get involved in that part of it. It happens typically at the, with our customers.
Yeah, but
Design
you're shipping that unit, and I'm looking at the fan and the way it fits in there and the wires you have, that could come apart unless you're really, really over making your product, which is okay too. It just costs more that way. So I'm just looking at the unit, the metal unit itself with the screws in it and that kind of stuff. That's what I like to do, is work on shock and vibration. So I was just wondering.
Yep. Yeah, we did a lot of that ourselves on our military unit, as you might well imagine. We did a lot of even sub-assemblies of our own unit.
Well, they have a lot of different shock and vibration for helicopters, tanks, Jeeps, that kind of stuff. But I'm just talking about how you ship that to your destination at this point in time.
Yeah,
They don't need military grade
right,
testing on that.
right. Yeah, that I know that we have I'm not involved in that part at all, so I can't really provide my feedback on it. I know that each one of these gets custom foam and they get boxed individually, and in many cases the CM is close by, and so we ship them on racks in plastic trays. Actually, the trays look like this. And so we'll ship racks of our equipment with foam inside, and the CM is relatively close by, so that works for longer distance, and certainly for the ECUs and the other. We have custom foam that surrounds the unit inside the box itself.
Like a foam in place?
Sort of. It's more like.
So it's just cut. It's not the foam in place.
Yeah, it's more. No, it's not foam in place. This one is glued in, but you can see they look kind of like that, only it's a stiffer foam than comes in these trays.
Yeah, you got to make sure the foam doesn't attenuate the shock of vibration into the unit. So I assume
Right.
you got someone that knows cushioning curves and that
Yeah,
stuff.
that's a bit outside my involvement. I'm all at the front end, and then I turn it over to engineering and then the packaging.
If you need a friend, you got Jan to call on.
When we return and when we get back to the cold chain, I definitely want to talk, because that's an area where not everybody has all the answers. And even the folks that come to us, they might have the electronics to do the tracking, and they can do that, but the packaging side itself and the experience with where to put the heat might not be there. And so those are things that we would need help with, and in many cases our customer would need help with that as well. So we'll definitely make a note to reach out.
And I know a lot of people that can help too if I can't. So
Thanks, Jan. Jim, have you had any, are there any medical device projects you can talk about that are maybe coming on board, or that you're working on, that were previously impossible due to the size of compressors and the like?
The one with the chemo cold cap could not be done with technology that what came previous to us. This system that is on the screen right now, typically there's no room for a 10-pound compressor in that unit. You know, they have both size and weight limits. So having two separate systems inside a unit that size was impossible before we came along. And before the willingness to integrate to a direct refrigerant, if this were a chiller, it would be twice the size and have 3 times the maintenance, because the compressor is going to last for 100,000 hours. The best pump will last maybe 30 or 40,000 hours. And the way one of our laser customers put it, if I keep using my chiller, my maintenance guy needs to be a plumber, because the liquid lines are prone to failure. They're not nearly as robust as the refrigerant lines. So not only would the system be less efficient if it were a chiller, it'd be higher maintenance, where the liquid levels need to be refilled,
Mhm.
and the lines are more suspect. And so by going to direct refrigerant, it's going to use 25% less power, or maybe less, than a chiller would. And even vapor compression chiller is going to use 4 or 5 times less power than a thermoelectric would under these conditions. So this is an example of something that could not be without the miniaturization of the refrigeration.
Before we wrap, and I don't know how many more slides you have, is there something a layman like me can understand about what your engineering insight was that allowed you to make a unit 1/10 the size of the one that you exerted yourself to pick up earlier in the presentation?
Certainly, what we did is we were driven by the requirements,
Real
or
layman terms here.
certainly in a need for small size. And so what we did is take a close look at which style of existing refrigeration compressor would be most amenable to miniaturization. And we spent a lot of time on the motor and settled on the little compressor here is a rotary vane design, been around for a long time, but we run it at 6,500 RPM. And that's where it's like running an Italian, the Italian sports cars they use high RPM small engine. That's sort of the analogy for what we did here. And a lot of work was done on the motor. Small, reliable, variable speed were all requirements. And so we use a brushless DC motor, variable speed, highly compact. We let it run up to 6,500 RPM, as low as 2,500 RPM. So we get a 3 times range in our capacity out of one unit. By coupling that with an expansion valve, it allows the system to react to a very wide range of conditions. So essentially, we went high RPM, used an existing compressor design, and put the motor technology together with it to run it at high RPM to get the refrigerant displacement that we need to get the high capacity.
We have a
And
question. An anonymous person asks, do you have any examples of an application within the MR environment?
MR,
I'm going to think radiology, and he or she can tell me otherwise if I'm wrong. I'm not sure who it is, so I can't call on them. So
everything is driven, the range of capacity that, the first question I would ask is, how many watts of cooling are needed? What's the delivered temperature? And the ambient temperature in this environment is probably about 22 degrees C. And then it would be, okay, that tells us how big the compressor needs to be. And then we work with the space that's given us to see if we can get it through the heat exchangers that can fit inside the equipment. So those are always the questions.
it is MRI, magnetic resistance.
Okay.
Magnetic resonance.
Okay, we are not doing that now. I don't have an application that is that, but it goes right back to cooling load and temperatures. And that tells us.
I can use her name. I can have Jim follow up with you afterwards.
Yeah, oh, I'd be happy to. Yeah.
Any other slides?
I've got a couple more applications. We do a lot of work in DNA sequencing. We did modify one of our standard product liquid chiller modules for this application, and we're developing full-blown chillers with the. Not everybody can use direct refrigerant, and many use liquid for a number of reasons. And in this case, we're developing a chiller, and we have another one in production that uses our liquid chiller module. And this is standard product. Let me see if I can get it in the screen here. You can see it. I'll just put it in front of my face. So that's about 6 by 8 by 5. It weighs 6 pounds. It'll do about 600 watts of cooling, and that's used in devices like that. And yep. So our liquid chiller module, and often our customers will start with a standard product. And what that does is it lets them get familiar with the controls, where the controls are driven by the company that really owns the medical device. And so we work on the control side. Often they start with one of these standard units to get things going in the R&D lab as we develop a custom configured system for the application. And basically talk to us about your application. This is my last slide here. So talk to us about the application. Call us with what you need. We may be able to come up with something you haven't thought of in terms of an approach to a solution. And this is just a very small slice across the types of things that the product development team is working on right now. But hopefully it'll trigger the imagination a little bit. And
Aspen, he's our anonymous attendee, Nathan Wang at Harmonic Medical. So I'll get you his email address afterward. Excellent.
Okay.
Well, thank you. And I knew none of this before, which is what makes these things so enjoyable to be able to
thanks for everyone who stuck around this long, and thanks for having us on here. Really, Joe, it's been a joy to pull this
follow
together.
presentation. Thank you, Jim, and I'll see everybody next week.
Thanks.
Thanks, Jim. Bye.